Hello and welcome to Equations. This is Neil. I'm a mathematician and a math educator. Through my video series, I try to teach mathematics in a way that is not usually taught in school. I hope that I will be able to show you the beauty of the subject and inspire you to fall in love with it. The great German mathematician Carl Friedrich Gauss once mentioned that mathematics is the queen of science, but number theory is the queen of mathematics. The reason Gauss said this was because he believed that out of all the different branches of mathematics, number theory was the purest and the most beautiful. And when it comes to number theory, the theory of prime numbers sits among the foremost in terms of beauty. And this is what we shall learn in this video. Prime numbers are the fundamental building blocks of all natural numbers. This is because every natural number can be broken down or decomposed into primes, as you shall see later in this video. This concept is very similar to the concept of atoms. If you recall, every element can be broken down into molecules and every molecule into atom. In a similar way, every natural number can be broken down into primes. To see this, let us first note down all the numbers. Say we shall write down all the numbers from 1 all the way up to, let us say, 30 or 31. So I've written down all the numbers from 1, 2, 3 all the way up to 31. What I'm going to do next is I'm going to circle some of these numbers with a different color. Let's say with a yellow color. I'm going to circle 2, 3, 5, 7, 11, 13, 17, 19, 23, 29, and 31. These are the first few prime numbers. These are the very first few prime numbers. To understand what makes a number a prime number, let us first write down the factorization of each of these numbers. For example, 1 can be written as 1 into 1, 2 can be written as 1 into 2, similarly 3 can be written as 1 into 3, but 4 can be written as 1 into 2 into 3. 5 can be written as 1 into 5. Again, 6 can be written as 1 into 2 into 3, and so on. If we continue this, we can write down any natural number as the product of primes. For example, 12 can be written down as the product of 1 times 2 times 2 times 3. Let us look at the factors of these numbers carefully. If you notice, some of these numbers have only 2 factors, while others have more than 2 factors. For example, the number 2 has only 2 factors, which are the number 1 and the number 2 itself. The number 5 also has only 2 factors, which are the number 1 and the number 5 itself. On the other hand, the number 6 has 3 different factors, which are the number 1, the number 2, and the number 3. So this gives us a hint. The numbers that are marked as prime numbers are those natural numbers which have only 2 factors, and these 2 factors are 1 and the number itself. On the other hand, numbers which are not primes, they have more than 2 factors. For example, the number 6 is made up of 3 different prime factors, which are 1, 2, and 3. Similarly, the number 4 is made up of 3 prime factors, which are number 1, 2, and the number 2 once again. So in 4, the factor 2 is repeated 2 times. Nonetheless, we shall agree with the fact that 4 is composed of 3 prime factors. The numbers which are not primes are called composite numbers. So to summarize, prime numbers are the numbers which have only 2 prime factors and they cannot be decomposed further into smaller primes. Let us learn about a very fundamental and important theorem of arithmetic known as the unique factorization theorem. To understand this theorem, let us write down the factors of 30. 30 can be written as 1 times 2 times 3 times 5. We cannot have any more factors of 30 because if there is a factor of 30 which is greater than 1, then the product of two times 3 times 5 and this new factor, their product would be greater than 30. Therefore, 30 has only 3 prime factors. Similarly, the number 31, it has only one prime factor because 31 can be written as 1 times 31. We cannot decompose 31 any further. So in this two example, what you are witnessing is that we can decompose a number into the product of primes in only one way. What I mean by that is you can write 30 as the product of 1, 2, 3 and 5 only. You cannot have any more primes, nor can you have any lesser primes. This is exactly what is known as the unique factorization theorem. The unique factorization theorem states that every positive integer can be written as the product of primes in only one way. We cannot write down a number as the product of primes in more than one way. There will be only one representation all the time, only one. Now that we are familiar with the concept of primes, so let me ask you, how many prime numbers do you think there are? The answer is there are infinitely many prime numbers, infinitely many. So, can you prove it? How can you prove that there are infinitely many prime numbers? It is very easy to prove that there are infinitely many natural numbers because whatever number I give you, you can just add 1 to it and you get a new natural number. But you cannot simply add 1 to a prime number or 2 to a prime number in order to get the next prime number. For example, if you add 1 to the prime number 31, you get 32, which is a composite number because it is divisible by 2. Similarly, if you add 2 to the prime number 31, you will end up with a composite number 33 once again. 33 is divisible by 3. So we cannot randomly add 1 or 2 numbers to the previous prime number in order to get the next prime number. So then, how do you think we will prove that there are infinitely many prime numbers? Surprisingly, the proof is very, very easy, extremely easy, and I'm kind of sad and it is rather unfortunate that the proof of the infinitude of prime is not there in any school books. It's rather a mathematical sin. I call it a mathematical sin that the proof of the infinitude of prime is missing from our textbook. So make use of this opportunity. I'm going to show to you a very, very simple proof that there are infinitely many primes. The proof is so simple that it was discovered more than 2,500 years ago when mathematics was at its very, very early stages, particularly arithmetic. And you need no more than school level knowledge to understand this proof. The credit of the proof goes to a Greek mathematician by the name Euclid, who's also the father of geometry. Euclid lived in the 4th century BC in Alexandria, Egypt. To understand Euclid's proof, we first need symbols to denote prime numbers. Let us represent the first prime number 2 by the symbol P1. The second prime number 3 is represented by the symbol P2. The third prime number 5 is represented by the symbol P3, and so on. In this representation, the nth prime number will be represented by the symbol Pn. Euclid then presents a very simple but extremely powerful and clever argument. He says, suppose that there are only a finite number of prime numbers and let the largest prime be Pn. Therefore, your set of prime numbers will contain the numbers P1, P2, P3 all the way up to Pn. Since we do not have any more primes, therefore, after Pn, our set of prime numbers stops. What Euclid does next is, he says, multiply all the numbers P1, P2, P3 in your set of prime numbers and then add 1 to it to get a number called capital N. So capital N is the product of all the prime numbers plus we add a 1 to it. This is the product of all the prime numbers, I repeat, plus a 1 to it. Then Euclid says, divide this new number capital N by all the prime numbers P1, P2, P3 up to Pn. Keep on dividing it one after another. Now, look carefully at the number capital N. If we divide it by P1, Capital N, it consists of two parts. The first part is the product of all the primes from P1 to Pn, and the second part is the number plus 1. The first part is clearly divisible by P1, whereas the second part is not divisible by P1. Therefore, when you divide capital N by P1, the remainder will be 1. Similarly, when you divide capital N by the number P2, the remainder will be once again 1. We continue this process and divide capital N by P3, P4, one after another, all the way up until we reach the number Pn. Even when we divide it by Pn, capital N will still leave a remainder 1. So we conclude that capital N is not divisible by any of the prime numbers from P1, P2, P3 up to Pn. None of these prime numbers divide the number capital N. But then, what does it mean when a number is not divisible by any of the known prime numbers? There are only two possibilities. Either this new number capital N is a prime number itself and therefore it is not divisible, or the second possibility is that capital N is divisible by some prime which is greater than Pn. In both these possibilities, we come to the conclusion that Pn cannot be the greatest prime number. Let me explain this once more. We have proved that capital N is not divisible by any of the known prime numbers. So it leaves us with only two possibilities. That is, either capital N is a new prime number, or capital N is divisible by a prime number which is greater than Pn. In both these cases, we come to the conclusion that Pn cannot be the greatest prime number. What it means is that whenever we are given a set of prime numbers, we can always find a new prime number which is bigger than the largest prime number in our set. So if we repeat this process infinitely, we will end up with infinitely many primes, because we will keep on finding primes which are bigger than all the previous primes that is known to us, and this process never ends. So Euclid gives us a very simple proof that there are infinitely many primes. This brings us to the end of this video. But as I mentioned in the beginning, the theory of prime numbers is amongst the most beautiful in the portfolio of the different branches of mathematics, and there are many more fascinating topics in prime numbers which we shall cover in the subsequent videos. So if you like what you are learning, do not forget to like, comment, and subscribe this channel. Thank you, and watch out for the next video.